In a submerged hull, the only stable reference is a spinning gyroscope. In the control room, the pilot lives by its needle because in pitch-black water there is no horizon and no fixed point, and the inner ear becomes a liar after minutes of turning in the dark. The gyro compass defines north, holds a heading, and keeps the boat a hunter instead of a drifting steel tube at the mercy of the currents. In the pre-dawn hours of December 7, 1941, inside the hull designated HA-19, that certainty vanished. The compass card wandered. The heading would not hold. The failure began before the mission truly did. The machine itself was a classified piece of naval architecture known as the Ko-hyoteki, or Target A. It was about 78.5 feet of black steel built for a singular one-way mission. Unlike standard fleet submarines, the Target A possessed no diesel engines and no generators for recharging its power cells. It was driven by a massive 600 horsepower electric motor, fed by a finite bank of batteries packed tightly into the hull. This propulsion system allowed it to sprint at 19 knots submerged, a speed nearly double that of conventional submarines of the era. However, this performance came at a ruthless price. The vessel had a limited endurance window. Once launched from the deck of its mothership, it was meant to strike and then rendezvous again. But the battery clock was unforgiving. It had to penetrate the enemy harbor, fire its 2 torpedoes, and then navigate to a recovery point on whatever charge remained. Every minute of operation consumed the energy required to survive. The launch sequence began about 10.5 miles off the harbor entrance. The mother submarine, I-24, surfaced under the cover of darkness to release the clamps holding the Midget sub to its deck. The crew of 2, a pilot and a navigator, climbed into the 78-foot cylinder. They were sealed inside a tube scarcely 6 feet across at its widest point, surrounded by high-voltage circuitry and compressed air lines. As HA-19 detached and slipped beneath the surface, the pilot powered up the navigation systems. The gyroscope should have spun up to speed and locked onto true north, providing a steady heading for the approach. Instead, the compass card drifted aimlessly. The heavy rotor had failed to synchronize. The pilot attempted to reset the system, but the device provided no usable data. In an instant, the tactical situation collapsed. The crew was tasked with navigating a narrow, winding entrance channel guarded by nets and destroyers, yet they had no way to maintain a straight course while submerged. The ocean floor in this region was not a flat plain of sand, but a jagged landscape of coral reefs and volcanic rock. Without a compass, the pilot could not execute the precise, timed turns required to slip past the outer defenses. The decision facing the crew was a stark trade-off between stealth and awareness. To know where they were, the periscope had to break the surface long enough to steal a landmark from the shoreline. But the water outside the entrance was shallow and patrolled by destroyers hunting for exactly that thin optical tube. Staying deep bought concealment, but it turned every correction into a gamble made on guesswork and seconds. With the gyro dead, the pilot chose to proceed. He tried to steer the Midget sub toward the harbor mouth using quick visual fixes on the dark coastline. But the currents wrapping around the island immediately began to shove the light hull off course. He fought the rudder, correcting wildly as he hunted for the range lights that marked the channel. And the boat began to weave in wide, erratic arcs. It was no longer a silent assassin closing on a target. It was a blind weight swinging through a minefield of coral heads. The electric motor hummed, pushing them forward at speed. But without a reliable heading, that energy was only driving them faster into the hazard zone. The weapon had become a liability, and the physics of the shallow water were about to take control of the mission. To turn a 78-foot steel cylinder in a narrow channel requires foresight, not reaction. When a submarine is submerged, it possesses momentum and mass that resist rapid changes in direction. The pilot must initiate a turn long before the obstacle appears in the crosshairs. For the crew of HA-19, this geometric reality became a trap. Without the gyroscope to maintain a steady heading, the pilot was forced to rely on visual navigation, a method completely unsuited for the turbulent, shallow waters outside the harbor entrance. Visual navigation imposed a lethal delay on every decision. A glimpse of shore became a calculation, a shouted correction, and then darkness again. In the seconds it took to complete that loop, the current slid the hull sideways. By the time the rudder bit and the boat began to swing, it was already out of position. The vessel was reacting to the ocean rather than cutting through it. The propulsion system added another layer of complexity to this erratic movement. The submarine was driven by two counter-rotating propellers mounted in tandem on the same shaft. This engineering design was crucial for stability. It canceled out the torque of the massive motor, preventing the narrow hull from rolling over onto its side when the pilot applied full power. While the system provided excellent straight-line speed and stability, it did not improve the vessel's turning radius. The long, slender aspect ratio of the hull meant it steered like a heavy train, not a nimble fighter aircraft. In the confined channels between the coral heads, the submarine was simply too long and too fast for the pilot to control by sight alone. The result was a series of violent collisions with the seabed. The first impact drove the nose of the submarine directly into a reef. With two 17.7-inch torpedoes and ballast concentrated forward, the bow tended to dig in. When the steel struck the coral, the shockwave traveled the entire length of the hull. The vessel shuddered and ground against the rock, scraping away paint and gouging the outer plating. The pilot threw the motor into reverse, the contra-rotating props biting into the water to drag the 46-ton machine off the obstruction. They broke free, but the orientation was gone. Every correction now cost battery time. At 2 knots, the boat might stretch to roughly 100 miles. At 19 knots, the cells could be spent in about 55 minutes. Each emergency burst, reverse, then full ahead to claw off the reef, stole more of what little charge remained. They were burning their power just to survive the geography. A second impact followed, then another, hard enough to warp frames and rattle internal components. The crew stayed at their stations amid ozone and groaning metal, but the blows were doing damage they could not see. Beneath the deck plates, in the tightly packed battery compartment, the violence cracked seals on the power cells. The battering would end, but the chemistry had already begun. The most immediate threat to the crew was no longer the reefs or the enemy destroyers, but the air they were breathing. Seawater worked into the battery compartment and sloshed across damaged cells, mixing with sulfuric acid in the cramped space beneath the deck plates. When seawater forces its way into a battery compartment, the atmosphere can turn poisonous fast. Lead-acid batteries flooded with salt water can give off toxic fumes, including chlorine gas. It is a heavy, choking hazard that does not simply vanish in a sealed hull. It burns eyes and lungs, and it can rob a crew of strength and judgment in minutes. The crew had no sophisticated scrubbing equipment to remove the toxin. Their only option was to endure the burning sensation while attempting to ventilate the hull, a near impossible task while running submerged in hostile waters and trying to avoid the destroyers hunting above. The physiological limit was reached quickly. The navigator and pilot were coughing violently, their vision blurred by tears and chemical burns. The coherent coordination required to pilot the vessel vanished. They were no longer calculating headings or monitoring the electric motor's temperature. They were fighting for consciousness. Largely uncontrolled, the submarine was carried east, away from the harbor entrance and toward the windward coast of Oahu. The logic of the mission dissolved. The objective shifted from attack to mere survival. The vessel finally succumbed to the geography on Oahu's southeast shore, near Waimanalo at Bellows Beach. It did not arrive as a conqueror, but as flotsam. The 46-ton hull snagged on a reef close to shore and then was hammered by the surf. The waves lifted the heavy steel tube and slammed it down onto the sand, over and over again. In the deep water, 46 tons has buoyancy and grace, but in the surf zone, it becomes a dead weight subject to the relentless pounding of the breaking waves. The relentless motion battered the crew, who were already incapacitated by the fumes. The interior was a chaotic tumbler of broken glass, tools, and toxic mist. Desperate to survive the gas and the physical battering, the crew made the final decision to abandon the machine. They opened the hatch, breaking the seal that had protected them from the ocean but trapped them with the gas. They spilled out into the dark water. The navigator drowned in the surf. His body washed ashore the next day. The pilot washed ashore, exhausted and unconscious, becoming the first prisoner of war. Behind them, the weapon remained. It lay rolling in the wash, a black silhouette against the white sand. It was a technological treasure trove for the United States Navy, sitting entirely exposed on a public beach. However, the machine was not quite dead. While the motor was silent and the crew was gone, One critical system remained armed and waiting. The pilot had engaged the final protocol before he leaped, initiating a sequence intended to turn the intelligence prize into twisted shrapnel. The difference between a strategic intelligence victory and a crater on the beach often comes down to the reliability of a single fuse. When the pilot abandoned the vessel in the surf, he had executed standing orders for the Ko-hyoteki class. He set the self-destruct charges meant to wreck the hull, ruin the torpedoes, and destroy the classified equipment inside. The pilot swam away as the vessel rolled in the waves, a captured prize that still might have been rigged to die. A naval salvage party from the submarine base reached the beach and found the Midget sub half in the shallows, silent but unmistakably hostile. They had no way of knowing whether a self-destruct charge still lurked inside. In theory, you secure the perimeter and wait for specialists. In practice, the surf was already threatening to tear the prize apart or drag it back into deep water. The decision was made to intervene immediately, accepting the risk to secure the prize. The self-destruct charges never did their job, and that failure opened the door to intelligence the United States Navy should not have had. Whether flooding, impact damage, or a simple misfire stopped the detonation remains uncertain. What is known is that American personnel later found the demolition charge and removed it before the submarine was moved inland. Unaware of this fortunate failure, the recovery team on the beach proceeded with the extraction. The physical challenge was the sheer density of the object. 46 tons of steel is difficult to move under ideal conditions. On a soft, sandy beach, with the suction of the wet sand gripping the hull, it was an immense engineering obstacle. The salvage team commandeered an army tractor, a piece of heavy equipment designed for earth-moving, not marine salvage. They waded into the surf to attach heavy chains to the nose of the submarine, working around the torpedo tubes that still contained live warheads. The extraction was a brute force operation. The tractor engine roared, the treads dug deep into the sand, and the chains pulled taut. Slowly, the friction was overcome. The 46-ton hull slid up the incline of the beach, out of the reach of the crushing waves. As it moved, the risk of a movement-triggered explosion remained high in the minds of the salvage crew. Every jolt or shift of the hull could have been the trigger for the dormant charge, yet the explosion never came. However, the tractor hauled the prize above the high tide mark and the vessel was secured. With the submarine resting on dry land, the immediate crisis was over. The salvage team had a largely intact enemy warship sitting on a public beach, miles from the secure facilities at Pearl Harbor. And moving it would be its own battle. It was too heavy for an easy haul and too awkward for the island's roads in one piece. To get it inland without destroying the evidence they had just risked their lives to save, the engineers would have to learn how it was built. The solution to the transport problem lay hidden beneath the black paint of the hull. As the engineers examined the 78-foot cylinder on Waimanalo Beach, they discovered a series of faint seams running circumferentially around the steel skin. These were major joins sealed with gaskets and held by bolted flanges. The vessel had not been constructed as a single, indivisible unit. It was designed with a modular architecture that allowed it to be split into 3 distinct sections. This design feature was the key to the salvage operation. It transformed an immovable 46-ton obstacle into 3 manageable loads that could be lifted by cranes and placed onto flatbed trucks. The salvage team set to work unbolting the heavy steel flanges. The process revealed the internal logic of the Japanese design. The forward section contained the torpedo tubes and the ballast tanks. The center section housed the control room and the battery banks, still reeking of the chlorine gas that had defeated the crew. The aft section contained the electric motor and the tail assembly. Once the bolts were removed and the connections severed, the submarine came apart in clean, structural slices. This modularity was not an accident. It was a necessity for a weapon system designed to be transported secretly to forward bases or carried on the decks of larger ships. The 3 sections were loaded onto trailers and driven to the Pearl Harbor submarine base. There, under guard and out of public view, the real autopsy began. The submarine was dismantled and documented in detail, its machinery and fittings studied and cataloged. Until this moment, the capabilities of the Midget submarine fleet were a matter of speculation and fear. Now, American naval architects could measure the hull thickness, test the steel quality, and analyze the propulsion system down to the last copper winding. The most shocking revelation awaited them in the stern section. The engineers uncovered a massive electric motor rated at 600 horsepower. In the context of 1941 naval engineering, this was a staggering amount of power for a vessel displacing only 46 tons. To put this figure in perspective, it meant the submarine had a power-to-weight ratio that allowed for explosive acceleration. It confirmed the terrifying performance statistics, a submerged top speed of 19 knots. This was nearly double the underwater speed of the standard American fleet submarines of the time. The analysis of the motor and the battery configuration painted a clear picture of the enemy's tactical doctrine. The designers had sacrificed everything for speed and stealth. There was no diesel engine for surface cruising, no generator to recharge the batteries, and no crew comforts. The 600 horsepower motor was a sprinter's heart in a gladiator's body. It was built to close the distance to a target rapidly, fire its weapons, and then use whatever energy remained to escape. The machine was not designed for endurance, it was designed for a single decisive strike. Further examination of the bow section revealed the firing mechanism for the two 17.7-inch torpedoes. The system was muzzle-loaded, a simple but effective design that saved space. Every inch of the interior was optimized for combat function. The survey proved that the enemy had solved the problems of underwater hydrodynamics and propulsion with a sophistication that matched or exceeded American capabilities. The mystery of the Target A weapon was stripped away. The United States Navy now possessed the blueprints, the performance curves, and the operational limits of the Midget submarine threat. The fear of the unknown was replaced by hard engineering data. The salvage operation had succeeded in capturing the hardware intact. The hull was cleaned, the damage from the reefs was patched, and the toxic interior was scrubbed. The machine was no longer a weapon of the Imperial Japanese Navy. It was a trophy. And like all trophies, it was about to be put on display. The engineers were finished with it, but the government had a new use for the hollow steel shell. The vessel traveled farther on the highways of the United States than it ever did in the waters of the Pacific. While its operational range was designed to be 18,000 yards at low speed, its final journey covered thousands of miles across the North American continent. The 78-foot hull, which had been built to deliver a stealth attack on Pearl Harbor, was mounted onto a heavy-duty trailer and paraded through the streets of major American cities. It was no longer a secret weapon, it was a traveling spectacle, marketed to the public as a captured enemy midget submarine. The United States Navy repurposed the captured machine into the centerpiece of a massive psychological campaign. The objective was the sale of war bonds, to finance the colossal industrial effort required to defeat the Axis powers. The government needed capital. The captured midget submarine became a primary tool for extracting that capital from the pockets of American citizens. Those same seams would serve one more purpose. They made the trophy portable. For the tour, sensitive components were removed, and viewing windows were cut into the hull so civilians could look into the cramped reality of the enemy's war machine. Crowds lined up in town squares and fairgrounds to buy war bonds for a closer look. The submarine arrived mounted atop a trailer, billed under a blunt nickname. They peered through the plexiglass panels at the tight compartments and the torpedo tubes, seeing cold steel proof that the war was not an abstraction. The narrative of the tour was simple and effective. It framed the sub as cold proof of the technology that had struck at Pearl Harbor. The irony of this second life was absolute. The mission of HA-19 had been to sink American tonnage. Instead, its capture and display generated the funding to build new aircraft carriers, destroyers, and submarines. The failure of the gyro compass and the saturation of the scuttling charge had inadvertently gifted the United States a financial asset worth far more than the steel used to construct it. The weapon ended up subsidizing the destruction of the very fleet it was commissioned to serve. When the war ended, the vessel did not face the scrapyard. Unlike the other 4 midget submarines sent in that morning, most of them sunk in the attack and later recovered, disposed of, or otherwise accounted for, this hull was preserved. It eventually found a permanent home in Fredericksburg, Texas, where it remains on display today. It sits in a quiet hall, far from the ocean and far from the coral reefs that tore its outer plating. The legacy of the vessel is not one of martial success, but of unintended consequences. It is a monument to the friction of war. A single mechanical failure in a gyroscope led to a blind navigation, which led to a reef strike, which led to a gas leak, which led to a capture. That chain of errors transformed a lethal predator into a museum exhibit. The pilot, Kazuo Sakamaki, survived the war and the prison camps, often described as the first Japanese prisoner of war captured by U.S. forces in World War II. To see his ship become a part of history, the machine stands today as a silent witness to the fact that in salvage and in war, the margin between a catastrophe and a trophy is often measured in inches.